This week in our lab we're going to be introducing another electronic device known as diodes. This is Lee Brinton and I'm an electrical engineering instructor at Salt Lake Community College. To understand diodes we're going to need to look at semiconductors and semiconductor physics at a very elementary level. We're going to talk about the crystalline structure of different types of semiconductors and how we can put impurities into semiconductors to give them or to make different types of semiconductor devices. In particular, we'll talk about the PN Junction, which is the most basic of semiconductor structures. And the most common application of the PN Junction alone is the diodes. So we'll be in lab today, this week, we'll be talking about diodes and analyzing diode circuits and then building them up and looking at how diodes respond to different types of voltages. Diodes are electric devices, as we've already talked about, inductors and capacitors and resistors. Well, a diode is another type of electrical device. They're used in a lot of different applications, such as rectifiers, which are electrical circuits that convert AC voltages to DC voltages. Diodes play a critical or a central role in power supplies and in voltage regulation. They're used to protect electrical equipment. They can be used in different forms of radio receivers. And then, of course, most recently, LEDs have become, which is a light-emitting diode. Diodes that emit light have become critical in electronic displays, televisions, and then also as highly efficient devices for illuminating rooms, replacing incandescent and fluorescent lighting. And they are also used in sampler and detector circuits. So throughout your electrical engineering career, you're going to run into a bunch of different applications of diodes, and all we're wanting to do this week is just introduce you to the diode and its voltage current relationships and give you a very basic understanding of them, and plus they're fun. They do interesting kinds of things. So conductors, non-conductors, and semiconductors. A conductor is a material that has lots of free electrons, and those free electrons, when placed within a voltage or within a potential field, those electrons are free to move. Now, generally speaking, the conductors that we've seen are metals. We've also talked about insulators, which are devices that don't have a lot of free electrons to move around, and so they don't carry electrical current even when exposed to a voltage. And those insulators then are typically glass, ceramics, plastic. We frequently will wrap them around a conductor to protect one conductor from another. But there's now a third type of material that we're going to talk about this week, and that's known as the semiconductors. Certainly you've heard of silicon and the Silicon Valley and the Silicon Revolution and all that kind of stuff. Silicon is one type of semiconductor. There are others. Germanium is one, and then recently you may have heard of organic semiconductors. But semiconductors are a family of materials that under certain circumstances they act as insulators, and under other electric circumstances they can serve as relatively good conductors. Now, looking at the periodic table, we know that the conducting metals fall within this mid-range of columns in the periodic table. Here we've got iron, cobalt, nickel, copper, silver, gold. So the best conductors fall right in this area here. The semiconductors are on over into this part of the periodic table. The ones that we're going to be particularly interested in are the semiconductors that fall within this 4A column. Silicon is probably is definitely the most widely used semiconductor substrate. But as we mentioned, you can also do them with carbon-based molecules, which leads into organic semiconductors. Germanium is one that we've also mentioned. So the semiconductors in general that we're going to be interested in as electrical engineers will fall in this region right here. Now, silicon. Silicon and the atoms in the 4A column all have 4 valence electrons. If you study the carbon atom at all, silicon has a similar valence electron structure to carbon. There are 4 outer electrons or valence electrons associated with each silicon atom. And it turns out that electrons like to be paired up. And so atoms of materials in this 4A column tend to bond to themselves in what are known as covalent bonds, where they actually share electrons between two neighboring atoms. So I've shown here a single silicon atom with its 4 electrons matched up with, and it actually forms a crystal, a very nicely regular shaped crystal with 4 nearest neighbors, and they share, each of them then sharing one of their electrons with their neighbor to form these covalent bonds. This is what we're going to refer to as pure silicon. Sometimes it's referred to as intrinsic silicon. There are no impurities in this, and one of the keys to making semiconductor devices is that the manufacturing processes have to be so pure that the impurities are almost non-existent. So natural or pure silicon is a non-electrical or a non-current carrying material. It's basically an insulator. But in the manufacturing process, it's possible to replace some of the silicon atoms with atoms of other materials. In this case, we're showing phosphorus. Phosphorus is in the next column over on the periodic table, and it actually has 5 valence electrons instead of 4 valence electrons. So when we displace one of the silicon atoms with a phosphorus atom, we take out the silicon atom with 4 electrons and replace it with a phosphorus atom with 5 electrons. So as it works out, there are 4 electrons from the phosphorus to form the 4 covalent bonds with each of the 4 neighboring silicon atoms, but there's that 5th electron that remains unpaired. And as such, this becomes an unbound electron that's free to move. And if we do that in enough of these, if we displace enough of these silicon atoms, we'll have an abundance of these unbound electrons, which can then serve so that doped semiconductor, the process of replacing silicon atoms with the phosphorus atoms is known as doping. And when the semiconductor has dopants in it, then we say it's a doped semiconductor, such that doped semiconductors, in the case where we've placed a 5 valence electron dopant in, has a surplus of electrons, and it can serve as a conducting material. Now we can also dope a semiconductor, the silicon substrate, the silicon crystal, with atoms that have only 3 electrons. In this case, I'm showing boron as the dopant, and once again we've displaced one of the silicon atoms from the crystal with a boron atom, only this time the boron atom has only 3 valence electrons. So boron in the periodic table is in one column left of the silicon and has 1 less electron. So these 3 here have formed covalent bonds, but this silicon atom here is short 1 electron, and there's actually a void in the electron structure of this bond. This void here is referred to as a hole. And so when we dope silicon with what we're going to refer to as p-type dopants, we're doping it with an atom that has only 3 electrons, and it leaves behind this void here, which are referred to as holes. So in this case, instead of having an extra electron, we're actually short an electron. And it goes beyond the scope of this class to really understand this concept of holes, but suffice it to say that an electron from a neighboring atom can actually break loose and fill this void, leaving a void over here, and then another one from over here can break loose and fill that one. And so in semiconductors, we can actually create a current using positively charged holes, if you will, or a current consisting of holes moving in a voltage gradient. So we can dope with N-type semiconductors, or we can dope with N-type dopants, such as phosphorus, that provides a free electron, and we can cause that to carry charge. Or we can dope with boron that creates a void, and in a similar way, placed under a voltage, we can cause the these voids to move from one point to the next and create a current which is known as a hole current that is analogous to an electron current, but it goes in the opposite direction. It flows in a different voltage direction. Now, some very interesting things happen when you create neighboring areas within a silicon substrate or in a silicon crystal where one part of it is doped with N-type, or the phosphorus that has 5 valence electrons, and then right next to it you'll dope another region with a P-type dopant such as boron that has only 3 valence electrons. This structure is known as a PN junction. And some very interesting electronics happens with the PN junction. The PN junction, it turns out, is the basics for the diodes. When we get into transistors, we'll see that there are multiple PN junctions involved in creating transistors, and but again, that relationship between the areas with a surplus of electrons and the areas where there's a void of electrons, there's some interesting electronic characteristics happen. Now, in the process of just creating this, in the manufacturing process, this separation of charge causes some charge movement that actually establishes a slight voltage that we're going to refer to as the junction voltage. The junction voltage is an inherent voltage within the PN junction that's established at the time the doping or the manufacturing process is completed. It has to do with the separation of charge. You've got P-type here and N-type here, and some movement. Again, it's beyond the scope of our class at this time. When we get into it in later classes, we'll understand it a whole lot better. But for right now, just understand that there's a voltage internal to the PN junction that's known as the junction voltage. We're going to see that when we apply a voltage to the device itself, we're going to have that external voltage be great enough to overcome that junction voltage before these devices will start carrying charge. So with that, we're now talking about, or we understand that we're going to use this PN junction in a device that's known as a diode. This is the symbol for a diode. It's basically an arrowhead with a line on it. It's meant to show and symbolize that current can flow through this device, but it flows in only one direction. Current will flow in the direction that the arrow is pointing. This line here is meant to suggest that current will not flow in the opposite direction. So, to cause this diode to conduct, and we can think of it as a switch closing so that the switch closes and allows things to flow through it, we're going to apply an external voltage with a positive voltage, the positive terminal of voltage connected to the P side of the diode, and the negative side of the voltage connected to the N-doped side of the diode. This side is sometimes referred to as the anode of the diode. So with this voltage applied, if the voltage is large enough to overcome that junction voltage that we talked about, we say then that the diode is forward biased. Now, bias means an inclination or is subject to. In this forward bias or this inclination, current then, positively charged current, is then free to flow from the positive dope side to the negative dope side and complete the circuit. So in a forward bias, the diode conducts. In the reverse bias, where we would put a negative terminal on the positive, on the P-doped terminal of the diode, and a positive voltage on the anode or the negative doped terminal of the diode, this junction that we talked about before is actually expanded, and there becomes such a large voltage here that we're not able to get electrons to flow through or current to flow through the diode. So under a reverse bias, we have effectively opened up the switch and made it so that current cannot flow through the diode. So just to review then, diodes will conduct when a positive voltage is placed across them. They don't conduct when the negative voltage is placed across it, and it serves effectively as a switch and can disconnect the terminals here. No current will flow through it. Now the voltage-current relationship in diodes is a little bit complicated, certainly more so than in the devices that we've seen up to this point. What this is meant to represent, and we've got the voltage along here and the current along this axis, we see that it takes that junction voltage amount, or the size of the junction voltage, an external voltage on the order of the junction voltage itself must be applied to overcome that junction voltage and allow current to start to flow. But once that junction voltage is overcome, current flows through it very, very freely, such that very small changes in voltage represent great changes in the current that can flow through. So we see a small change here gives us large changes in current flowing through it when the diode is forward biased, or that there's a positive voltage across it. On the other hand, when the external voltage is not large enough to overcome the junction voltage, or in fact is negative, very, very small amounts of current, in fact we're going to say that in the reverse bias no current is flowing through it, up to a point, and of course if you push it far enough the diode will break down and allow current to flow. But for our interest in this class, we're going to be talking about moving the diode from an off position into its forward bias and seeing what happens when current is allowed to flow. We've already talked about the symbol here. There are a number of different types of diodes that we'll be using in electronic circuits, including LEDs. And those are kind of fun because LEDs, of course, glow when they're in the forward bias and allowing current through them. Now this model here, or this voltage-current relationship, is actually an exponential relationship where the current is equal to some initial current I0 e to the, we'll just call it V. We'll just leave it at that for now, so that what we're representing is that the voltage across here is raised to the power, is the exponent in this function, and the very small changes in V represent very large changes in current. And this is the best model that's out there. But gratefully, we don't have to go through that exponential model in order to use and to analyze diodes, at least not for a quick and dirty analysis in the laboratory. So in the laboratory, when we're doing analyzing circuits, we're going to think of them as either ideal diodes that will have no voltage drop across it, but as long as there's a positive bias, any amount of current will flow through that the circuit around it will allow to flow through. So the ideal diode model suggests that, or models the diode as a zero voltage drop across it. We've got the diode. It's involved in a circuit that has a battery or some sort of a power supply associated with it. In the ideal diode model, we will be saying that the voltage across the diode is 0 volts. In other words, there's no voltage drop across the diode. In reality, we know from that previous slide that there is some voltage drop across it, and it's exponential in nature. But again, for quick and dirty calculations in the lab, it's very convenient to use what is known as the constant voltage drop model, where we identify a point in this curve where the diode is well into its conducting region, and whatever that voltage is there, it's of course that threshold voltage that we've talked about previously. We're going to simply say that we're going to see a constant drop across here, independent of the amount of current flowing through it. Now for electronic diodes, the diodes that we'll be using generally speaking in the lab, it's a good estimate to just say, well, that's going to have a 0.7 of a volt drop. Those voltage drops are usually somewhere between about 5 0.1 of a volt, 0.5 volts, and 0.75 or maybe 0.8 volts for typical signal type diodes. LEDs, on the other hand, light-emitting diodes, actually have a junction voltage up around 1.5 volts and sometimes as much as 2.5 volts, such that it takes an external voltage of 1.5 volts to 2.5 volts to get current flowing through the diode, or to get the diode into its conducting region. We determine which of these two models to use by identifying how much accuracy do we need. If we're looking just at a very qualitative understanding, just kind of what is happening, the ideal diode model is plenty adequate. If we're looking for a little bit better, actually wanting to do some current calculations, we may then choose to use the constant diode model. In future classes, when we actually get into simulating the diodes, we'll use that exponential relationship between voltage and current.